We show how image-based and geometric warping, radiometric compensation and multifocal projection enable a view-dependent stereoscopic visualization on ordinary surfaces within everyday environments. Liquid crystal shutters in front of each projector lens support an active stereoscopic projection. Infrared camera tracking provides the position and orientation of a camera or a moving observer. Projected structured light enables the computation of a pixel-precise mapping between camera space and projector space for every camera position. A geometric map can be derived from this. In addition, the surface reflectance, the environment light contribution, and the projector's form factor components are measured for each camera position. An image projected onto a complex surface, like this natural stone wall, can be corrected for a single viewpoint. The surface seems to disappear. However, if the observer moves away from the calibration camera, image distortions become visible. Using our unstructured view-dependent approach, the image can be observed correctly from arbitrary positions. This shows the image correction performed for a moving user, but observed from a static camera position. Having depth information on the surface, correct occlusion effects with the real environment can be created. Images that are not color compensated are blended with the underlying surface. A fusion of stereo pairs, and consequently a correct depth perception of the displayed scene, is difficult under this situation. An adequate radiometric compensation solves this problem. Here we show an architectural walkthrough projected stereoscopically onto a natural stone wall. Color and geometry of the images are corrected. The background of the scene has been stenciled out and is intentionally not color compensated. This allows seeing through the 3D model wherever possible, giving a sense of the real environment. The effect provides a consistent spatial perception of the virtual and real environment. The final result is similar to a common stereoscopic wall light projection. The human visual system strongly relies on the extraction of structural features for estimating disparities. For uncorrected projections, the features of the underlying surface can be dominant over the features in the displayed images. In this case, the depth perception is not consistent. A per-pixel radiometric compensation that neutralizes the blending artifacts on real surfaces is essential for visualizing stereoscopic imagery on the textured surfaces. This shows a corrected projection on a papered wall. Stereoscopic visualizations can quickly be realized in everyday environments, such as in this concrete basement, in which the register structure of an adjacent room can be shown for architectural applications. This example shows a CAD model of a stairway projected stereoscopically onto the floor. Looking down allows the lower level of the building to be seen. Conventional projectors can only focus on a single focal plane. When projecting onto a complex 3D surface, the varying depth can cause blurring effects. This washes out the image features that are needed for correct depth perception. Here we show an experiment with two extreme off-axis projections onto a plane. For each projector, we can measure the focus error on the surface on a per pixel basis. These errors are visualized here for two off-axis projections onto a common planar surface. A final image with minimal focus error can be composed from different projector contributions in real time. Our techniques enable a view-dependent stereoscopic projection in everyday environments and on ordinary surfaces. Special display configurations for immersive or semi-immersive VR and AR applications that require permanent and artificial projection canvases might become unnecessary.